Okay, this is the second part of the organohalide lecture topic. This is where we ended up last time. We were just talking about other possible factors that contribute to the reactivity of organohalides and possible changes in mechanism, for instance. So here we have a primary halide. This is a benzyl bromide reacting with aqueous potassium hydroxide. The hydroxide ion is going to act as the nucleophile in the reaction to give us benzyl alcohol and KBr as a product. We would expect this reaction to occur via an SN2 process because the organohalide is primary. It's a primary substitution. It's not very heavily substituted around here, so we wouldn't expect a hindrance of the nucleophile attacking the carbon to make the bromine leave. So we'd expect an SN2 reaction. However, we get an inconsistency. The rate equation for this reaction is only dependent on the benzyl bromide. So what's going on? Because we should see a bimolecular dependency. What's thought to be happening here is that the pi system adjacent to the carbon bearing the bromine is having an effect on it's two things. It's having an effect on the carbon-bromine bond, such that the energy barrier, the transition state for reaction via a carbocation to products, is going to be lower than the energy barrier for an SN2 process, which would look like this. So let's go through that again. An SN2 process would proceed, in this case, with a higher energy barrier. But it turns out that the SN1 route has a lower barrier, and this is thought to be because of the pi system. Here, the carbocation in the reaction is very, very stable because of aromatic delocalization across the pi system, and the stability of this carbocation pulls the transition state lower than the SN2 route. That explanation is, if you think about it, is a bit chicken and egg, whereas this is the chicken and this is the egg, but I'm using the carbocation stability argument to say that the transition state is lowered, but that's the way people discuss this type of effect. The vacant 2p orbital next to the pi system results in a aromatic carbocation that's delocalized and stabilized. The electron density in the system looks like this. We would expect to see much more red on this area and maybe a blue on this area, but what we see is a yellow-orangey distribution that goes across or the surface of the carbocation. We're going to talk about the nature of the leaving groups in these chemistries, because we don't have to have a halide leaving all the time, and we're going to talk about the incoming nucleophile and the synthetic utility of the chemistry. So incoming nucleophilic groups don't have to be hydroxyl or ethoxy, but these are the sort of groups that you will see at A level or previous to the degree level. They can be, I'm saying using the word exciting as much as anything can be exciting, but I'll try and excite you. They can be carbon-based nucleophiles, like these are, or they can be heteroatom-based nucleophiles such as amines with no charge on, just to remind you that all that we need from a nucleophile is an available lone pair of electrons. So here we have the cyanide group. Now the cyanide group would be the nucleophile. It comes in and attacks here if it's an SN2 reaction, or cyano groups can substitute via SN1 as well. The leaving group can leave, and we attach the nucleophile to the carbon framework. Now the negative charge is born on the carbon in this case, so we end up with a new carbon-carbon bond and a cyano group attached to this. And cyano groups, as we've met with amine chemistry in the previous set of lectures, are synthetically very useful, particularly for drug synthesis. Our carbon-based nucleophile can be a deprotonated acetylene, and this is one of the exercises I gave you back when we were talking about alkynes, to have a look at this type of chemistry. If you don't remember, go back and have a look at those notes. The Grignard reaction, the Grignard reagent, Grignard chemistry can be regarded as a carbanion, and a carbanion would act as a nucleophile and attack this system to cause Y to leave in some circumstances. And again here the nitrogen can attack at the carbon, cause Y to leave and give us a substituted amine. And subsequent chemistry. Look back at the amine chemistry to remind you what might happen in that case. The leaving groups, outgoing or leaving groups, don't have to be halides. They may be things that behave like halides and are often referred to as pseudo-halides in very loose terms. These are just two examples. The one on the left is known as the mesylate, M-E-S-Y-L-A-T-E, because it comes from mesyl chloride, which is an acid chloride. If you use that acid chloride to react with an organic compound that's got an alcohol here, you end up forming a sulfonate ester, and that sulfonate ester becomes the Y group, and then our X will attack here and the whole of the Y, this, can leave. Have a look at the appropriate literature to expand on this a little, but there is a link here to discuss it a little further. This is the tosylate group, and this comes from the reaction of tosyl chloride with alcohols to form a tosylate, which is a sulfonate ester, and this group is the Y group that leaves. And both these behave a little like halides, even though you can obviously see there's no halogen bonds in there. The entity with its electron pair behaves like a halide, and therefore they're sometimes referred to as pseudo-halide groups. Stuff to do for the student. The student should be expected to be able to recognize a simple organohalide and name it. That comes from Dr. Ball's lectures. Recognize whether it's primary, secondary or tertiary. It could be chiral, and you should be able to assign that stereochemistry. Again, Dr. Ball would have covered that with you. There are stereochemical consequences for reactions with variously C-substituted halides. Be able to understand what determines mechanism shifts in a homologous series. Methyl, ethyl, propyl, isopropyl, butyl, isobutyl, tertiary butyl. Phenyl, we know what happens with phenyl halides. Look back at that chemistry when we did aromatic compounds to remind you. And benzyl, what would happen in a benzyl system. Recognize lone pair bearing nucleophiles of various types. That requires enough background reading to maybe pick up a few more nucleophile types and be able to predict their products. Realize the synthetic value of these reactions. You should be able to, in any discussion about alkyl halide chemistry or organohalides and their usefulness, you should be able to say how you think the chemistry might be useful for synthesis, particularly in the context of drug synthesis, or at least going towards drug synthesis. Now we're going to turn our attention to a different aspect of organohalide chemistry, and that's addition and elimination, just to remind you about this chemistry. So if we take an alkene and we add a polarized XY molecule across it, this would be an addition reaction. We've met this before. If you, however, reverse the chemistry, in other words, take the elements of X and Y away from the system, that would be referred to as an elimination reaction. And we haven't done much on elimination before, but we have mentioned it slightly earlier. But this is really just a reminder. So if we take our cyclohexene and add HBr across it, we would get cyclohexyl bromide. That's an addition reaction. The chemistry goes via attack of the H plus or polarized HBr on the double bond. It would cause addition of a CH, appearance of a CH group in the molecule and leaving of Br minus to give you a carbocation at this point, and then the Br minus comes in and attacks the carbocation to give you an addition across the double bond. If we look at a substituted cyclohexene, which is what this methyl group's doing on that double bond, it gives us an additional substitution on the double bond. This is just a reminder that you can have major and minor addition products across the double bond that are determined by Markovnikov's rules, which we met earlier in the course. Elimination reactions. So if we take our added products, HBr across the cyclohexene ring to give us the cyclohexyl bromide. Cyclohexyl bromide can have its chemistry reversed to give you the alkene with removal of water and the restoration of KBr by the addition of a strong base, potassium hydroxide, and suitable solvent, in this case ethanol. The reaction is an elimination reaction. Now what happens is something probably reasonably counterintuitive to most students. A strong base will attack the beta position, hydrogen, next to the alpha position that bears the bromine. This pulls this hydrogen off, releasing a pair of electrons to go in between these two carbons and causing a bromine to leave, and that results in elimination and reversal of our addition. This is just to remind you that elimination reactions don't have to only occur with organohalides. They can occur with alcohols as well. And remember when we talked about hydration of double bonds by addition, I did also mention that reaction can be reversed and an elimination can occur. And actually some of you may well have done this in the laboratory previous to coming here. So if we take this methyl substituted cyclohexanol, we've got phosphoric acid acting as an acid attacking the alcohol. It's normally undertaken with a little heat. We get protonation of our alcohol, and our protonated alcohol leaves as water to give a carbocation. The carbocation is looking for a pair of electrons. If it gets it from water, it won't get it from this system because this is actually delocalized. If it gets it from water, you get a reversal of the reaction. If, however, it's trying to grab a pair of electrons to satisfy its valency, if it gets it from this CH bond that's adjacent, and you have to have a hydrogen on the beta position to the carbocation, you get an elimination reaction or dehydration, and the H plus goes back to the phosphoric acid. Therefore phosphoric acid is a catalyst. And just to remind you, because it's an equilibrium, depending on the reaction conditions, you can reverse the chemistry to go from an alkene to an alcohol. Okay, so we've finished the second part of the organohalide chemistry with also a little bit of revision on addition and elimination, and this should put you in good stead for any questions in the end of the unit exam on this topic.